You can see the simplicity of what we face as long as we stick with a one-dimensional situation. But it is important to remember the general definition of both the composition and the inverse. Okay, so that probably still will appear on your homework a few times before we move on to more advanced things. So the arrows are very helpful if you're wondering about how things work. This is how you can actually have examples of with marks and how you can the composition is consecutive arrows like this. Like this. So if this is F and this is G, and then you have elements, whatever they are, and then how do you find the composition? You do it one by one, and you follow the arrow like this, 2 arrows in a row, or like this, arrow in a row, 2 arrows in a row, and that will give you from the input of F to the output of G all the way through. Okay, so that's how compositions work. Okay. Okay, so we started the next one. Okay, so the next topic is the big one. This is where linear algebra comes from, and that is, for the most part, is solving linear equations. As simple as that. So solving linear equations. Well, of course, it's easy. Okay, so in one-dimensional case, that's pretty much the example of a linear equation, and this is how it's solved by division. So even if in general mx is equal to b, m not equal to 0, as long as then you have x is equal to b over m. Okay, so just division gives you the answer. And if m is equal to 0, then, well, no solution unless what?
B equals 0.
Yeah, b equals 0, that's right. So as you can see, there are 3 cases, and that will pretty much continue to be the case. One is when this slope, or whatever you call it, this multiple on the left, is not equal to 0, then you are, so okay, if m is not equal to 0 here, not equal to 0, and if m is equal to 0, then we have a different situation. So 3 cases. One, if m is not equal to 0, then what we're facing is one answer, one solution, one only solution. In the meantime, in the second one, it is equal to 0. Then there are 2 possibilities. When only then we look at the right-hand side, and the right-hand side is b, and that determines it. So once again, so m not equal to 0, one solution. B is equal, x is equal to b over m. Okay. So now m is equal to 0. One possibility is when b is not equal to 0. Right? So then no solution. Why? Because you see what's happening. So m is equal to 0, b is not equal to 0, then you have a contradiction, right? So 0 is equal to b. That's a contradiction, so no x will satisfy this equation. That's it. Now, if m is equal to 0, but b is also equal to 0, then what? X is any number. So 0 is equal to 0 is the equation we end up with. And then all numbers are solutions. So that's an easy classification of linear equations in dimension 1. 3 possibilities, and what is it? 1, none, and infinite. So these are the 3 possibilities. Think about other equations, nonlinear equations that you have seen, and you realize that that's not gonna. It's never this simple. You can have, say, x squared is equal to 1. You have two solutions. You have x cubed is equal to, I don't know, x squared minus 1, something like that. Then you might have up to 3. So infinite solutions is not even a typical situation. But for linear equations, that is a typical, once again. 1, none, infinite. So it will be slightly more complicated than that, but it will be by far more complicated than that, but the basic classification will remain the same. So a 1 non-infinite number of solutions. So let's look at dimension 2. So this is dimension 1. Let's look at dimension 2, and I want to do an example. I'm going to do an example in order to emphasize something, the part of the course, and that is the ability to translate situations. Well, pretty much, let's just say these are word problems. So word problems, translating them into mathematics, then solving them. And this is the problem that I want to present. So we have a first type of coffee. Is $3 per pound. Okay, and the second one the other way. The first one is 2, the second is 3. Okay. So the question is, how much of each type do you need to have 6 pounds of a blend with a total price of $14? So how much of each do we need for 6 pounds of blend worth $14? Okay, so that's the whole problem. Translate. Let's translate.
4 of 2 and 2 of 3.
4 of 2 and 2 of what?
Like 4 times 2 plus 2 times 3.
I don't think so.
Mm-hmm.
Well, first of all, let's not jump to solving the problem. I don't want to solve the problem. Solving the problem is so much less important than actually understanding what the problem is.
Okay.
So, and the point of word problems is always the same, is to the ability to translate the problem itself, not the solution, which you might guess or not, into algebra. So how do you do it? You introduce variables. You introduce variables, then you translate all the statements that you have into algebraic operations between them, and then once you're done, you have a nice, probably a much smaller, compact problem, algebraic problem that you solve. Okay. Okay. So there are unknowns, or one unknown or many unknowns. So we call them by letters. So usually start with the word let. So let x be what?
2 pounds of the first type of coffee.
Yeah, that's right, pounds of the first type in the blend. That is, you're pretty much starting from the end. The end is how much of each, and that is the first thing to address. That will tell you what your variables, the unknowns are. So these are the unknowns. And when you already know the unknowns, well, you will usually give them letters such as x and y in the blend, and then y of the second type. So the number of pounds in the of the second type of coffee in the blend. Okay, so these are the only quantities that we need, and we might not need anything else. Okay, so So then the remains is to continue to translate. This is like a dictionary for translating from one language to the other. And now we take that little problem and translate it using this this dictionary with only 2 entries, and just take the statements. So starting from, okay. So what's next? Okay, for what? For the price and the number of pounds. That's right. So first equation. So is for the weight, say. So what part of where do we see that? It is right here, 6 pounds of blend. Okay, so if I take this, what does the equation look like? X plus y is equal to 6. Okay, and then the next one is it's worth $14. Yeah. 2x plus 3y is equal to 14. Okay. Okay, so that is all we need. Let's now state the problem. So let's say algebraic problem. What problem has become an algebraic problem? So find all pairs xy such that x plus y is equal to 6, 2x plus 3y is equal to 14. Okay, so for find all pairs, that is usually translated as solve. Solve the system of equations. So the system of equations is something that we'll learn to use freely, but at this point it is nothing but terminology. So what I did right there, find all xy such that they satisfy these equations, is really what's happening. So it's better to think about what's going on rather than find a good name for it. Solving an equation or system of equations is a good way to describe it, but really we need to remember what it means. And what it means is find all pairs x and y, satisfying those equations. One thing I want to add here, important, is the first equation has to be satisfied as well as the second. Okay, so so let's proceed from this point, and let's do like pre-calculus level solution. So solve it. How do we solve it?
Take the top equation,
Yeah.
multiply it by -2, and then add it to the bottom equation.
Okay, so that's fine. So multiply equation 1 by -2, add 2 second. Okay, so it will be negative 2x minus 2y equal minus 12, right? 2x plus 3y equal to 14. That remains the same. And then I do addition. So the first two cancel out, and I'm left with y equal to 2. Okay? Is that it? Now x, so I use maybe the first equation. Equation 1, I have x plus y, which is 2 is equal to 6. So x is equal to 4. Okay, so how do I write the answer? Is simple. I could simply write x equal 4, y equal 2. Or on our next level, how would I write the answer? It is what? As a pair. As a pair, that's right. So I would write 4, 2. So why 4, 2 first? Why are we talking about pairs, and what's the advantage of that? Graphing, right? So let's graph. So these are actually points x, y that we're talking about, and has been purely algebraic, right? But we can visualize these because x and y's are x coordinate, y coordinate, or the point x, y on the plane. Okay, so then we can understand what these two equations stand for. So x plus y is equal to 6 looks roughly, so this one looks roughly like this. X plus y is equal to 6. First of all, we talked about early on. Both of them are lines. Okay, so if we now examine geometry of this, is x plus y equal to 6 is a line, a straight line. And the other one, 2x plus 3y is equal to 14, also is a straight line. Okay? So, all right, so we plot one, we plot the other, and then what? What's the point of plot? And we'll find the intersection. The intersection will be the answer. Okay? So, let's see how to plot the other one. When y is equal to 0, x is equal to 6. So we are here somewhere. That's the other point. And so this is 6, this is 6, and this is 6. And then to here somewhere, like this. Okay, so this once again 6. These are the 2 points, the x and y intercepts of the first equation. This is the second. 2x plus 3y is equal to 14. Okay, and the solution is right here. 4, 2. The solution. Okay, so all right, so that's fine. Let's however try to connect this idea. So let's forget about where the problem came from. It is the problem we're facing and going to be facing a lot is systems of linear equations. This one, system of two equations, two unknowns. Even though, once again, recognize the advantage of thinking about the system of equation, even though there are two equations, but you can think about the solution as a point, one point, not two numbers, but it is a point. It just happens to be on the plane, and that is very very advantageous. And then your understanding of solving equations will be very much useful, as we see in a moment. If we go back to our classification of right here of single equations, one equation, one variable, mx is equal to b, and we are in a similar place right now. Except we have an equation of two variables, two unknowns. But they are linear. The lines are linear, the functions are linear. So once again, we talked about that just a little bit, but you remember that as you can see, both x and y appear in a linear fashion. So there is no squaring of x or y, and there is no multiplication of x and y. So that's what makes them linear. So these are linear functions of two variables each. Okay, so the hope, and that's the big plan, is to actually try to come up with a way of looking at our system of linear equations the same way as we look at the system of one equation, one variable, one equation versus two variables, two equations. Certainly, the complexity has gone up by a lot, but that's the thing. You don't want to avoid the complexity and try to reduce everything to the simple algebra. Why? Because we want to understand it. We really want to understand it because it's easy to imagine that we were able to handle this problem fine, but imagine that we have another mixture problem with maybe 3 types of coffee. Okay, and you still might ask the similar question about you have the 3rd type of coffee, and maybe it is worth $4 per pound. Okay, and then you want to mix them up into, once again, a blend of $14 worth, 6 pounds altogether. Okay, so you'll have, what will we have here? 3 variables, x, y, z, and how many equations? How many equations if you have 3? Well, from what I said.
6.
No, equations. It's still 2, right? So the same restriction. So it is possible to have more variables than equations. Okay, so right now we don't care about that much because that's three-dimensional situation. This is two-dimensional situation. You already can see that it is typical to have naturally two equations, two unknowns as we have. But you can also imagine that, well, just throw out one of the equations and you have what? You have two unknowns in one equation, and then there is a relation between them. And then you can see the similarity with the previous situation. What if I have only one equation left? How many solutions do I have? X plus y is equal to 6. Let's say I'm left with this. X plus y is equal to 6. What?
Can you make maybe some more relationship you have to separate those?
Oh, well, how many? So the system of equations now still has two variables, but now it has only one equation. How many solutions do we have? Infinitely many solutions, right? So just like in that situation, we had one-dimensional cases. How do we know it's infinitely many? Every point on that orange line is a solution. Okay, so there you go. We already have similarities with one-dimensional situation. So we have a case of one solution, right? Two equations, one solution produced to us. You can think of one equation, two unknowns, or I could do the same trick as I did last time, like this. I have two equations, and might not be obvious on the surface, but how many solutions? It's the same equation, right? It's the same equation, and we still have infinitely many solutions. And here we have a single solution. Okay, so can you think of a system? What's the third possibility? No solutions. Can you think of an example? If I start with x plus y is equal to 6, can you think of another example which would give me no solutions?
X plus y equals 5.
X plus y equals 5, that's right. So no solutions. Okay, so as you can see, we have once again for the classification, very loose classification has now the same three possibilities: one solution, no solution, or infinitely many solutions. There is a more extreme case of infinitely many solutions. It is when every pair x, y is a solution. So when the equations really totally disappear, just like you end up with 0 equal to 0, it is not just infinitely many solutions, but every pair of numbers is a solution, right? So just like in the one-dimensional case, because that case on the left is not as extreme because some of the x, y's are not solutions, right? So for example, this point, if I'm looking at this example again, this point is not a solution, and that point is not a solution. Only points on the orange line are solutions. Okay, so that's less extreme, and that will be more and more typical as dimensions grow. There are more possibilities of having infinitely many solutions, but there will be still only one possibility for having a single solution. So that's geometry, and it suggests the way we're gonna proceed. We're gonna proceed to high dimensions. Then we proceed to three variables and maybe three equations. You can guess what an equation of 3 represents. Represents the three variables. Say what is this? You think?
3D.
What?
3D.
Yes, it is in 3D, but what does this equation represent? If you can guess.
A sphere?
What do you say?
A sphere?
Not quite. I mean, it's not going to be curved, right? Everything is linear. So the sphere,
A cylinder?
no, still curved.
A box or a cube?
No, or close. What's on curved? What? On curved surface. That's what we're talking about. So you listed surfaces, but they are all curved. You know, they have curving. A plane, right? So so we're going to have planes. And then that's the tricky part. You can see how geometry becomes more complex. You have a bunch of planes, maybe 2, maybe 3, and then what we're looking for intersection. So if you take 2 planes, the intersection is probably a line unless they're parallel. Okay, and then so all of those cases, and then when you have three planes, they might intersect by a single point. Think the one plane is that wall, the other plane is that wall, and the third plane is the floor. The intersection is that corner over there. So the one point. It is a typical situation. If you pick randomly three planes in space, they probably will intersect at one point. But it's possible that they can be parallel, such as ceiling and the floor. And there are all kinds of arrangements that might look kind of nasty, like triangular. They're not parallel, triangular. How should I put it? Like this. So one horizontal plane and two sloped planes. And what's the intersection? What?
Like 3 lines.
No. Well, you have to understand what intersection means. It means where all three meet together. Remember, the equation has to have to be satisfied simultaneously, all of them, not just one at a time, not two at a time, all three at a time. So what's the intersection of all three? What? Yeah? There is no intersection. So in that case of we have a no solution independent solutions and one solution. So that is geometry, and we'll get to that. But you can see the limitations. That dimension 3 is fine, but when you go high in dimensions, we cannot visualize anymore. So we have to learn as much as we can about geometry with the dimensions 2 and 3, and then we'll kind of give up because we cannot visualize anything in high dimensions. And the mixture problems, the example I would like to offer every time in high dimensions. So a portfolio with you buying stocks, and you might have 100 stocks. Okay, and you have this much money. And you want to put stocks depending on, there are some restrictions. The restriction is the amount of money, but maybe also depending on different circumstances, there are other restrictions on the amount of each of the stock that you can hold and the proportions between them, and God knows what else, possible regulations or just your decision making. The point is that there will be 100 variables. So each stock can be owned or not owned, and a different value can be assigned to it. So, and then you mix together, your portfolio becomes a mixture of these stocks, and then you have to decide which whatever you decide or not, you have to figure out how much to hold, and that amounts to solving a system of linear equations in dimension 100. Okay, so of course, if you want to hold every stock, the stock exchange, it might be 10,000. Okay, so or you do it with commodities, the same thing. So all kinds of mixtures. You try to deal with futures or future or past or insurance or double or derivatives, or God knows. So once again, you mix things together, and that's the thing. They're mixed in a linear fashion, right? So the amount X is the amount of particular stock multiplied by its price, gives you the worth of your portfolio, and since you're buying, that probably number is fixed, but then there might be extra restrictions which I don't want to contemplate. But the point is that it is the situation can be easily multi-dimensional. And then of course, if that's high-based stock exchange, you can think of any other circumstances. How about machine learning? They collect data without giving it a lot of thought. So, for example, they teach the machine to recognize numbers, for example, without trying to explain what number is. So they show pictures to the machine, and then what does the machine? And then they do measurements of those pictures. So they might be the number of black pixels, the number of white pixels, or gray, or adjacent to each other, and see what happens. And then they might produce easily 100 or 10,000 numbers. And once again, they vary, and then each image then lives in this maybe 1,000 dimensional space. And once again, you do stuff with it. At the easiest, it will be linear. So the relations will be linear. Okay, So the point once again, so we have to, sooner or later, we have to go back to algebra, unfortunately, and because we won't be able to visualize everything every time. So we're going to have, our best hope is then to end up with something like this. Mx equal b over there. So, but in a multidimensional case. So as you can see, even in dimension 2, there are just too many variables to handle. Geometry at some point will be out of the question. So at this point, what we're trying to do is just to collect the data and put it in a compact form, even when you have a multidimensional situation. And the answer is vectors and matrices. Okay, so let me quickly do that for this particular problem. So we're the equation right there. This is my system of equations, and I want to just extract the information from this system of equations and put it in a compact form that would look like mx equal b. So let me start over. So mx equal b ideally is what the one-dimensional linear equation looks like, and I want a similar. I want something similar, except my equation looks quite a bit more complicated. So what is it? X plus y is equal to 6. 2x plus 3y is equal to 14, right? So that's my system, and that's and that it can be. So that's the form that we'll pursue, and that the real data that we are facing. So we want to find just a new form to represent this system of equations. One idea is already there. It is the xy is a point. Except this time we're not going to be thinking about xy as a point, but rather we're going to think about it as a vector. Which the difference is not that important at this time. So easy to visualize, say this point, say 1, 3. You can think of it as a point, or you can think of it as a vector, which is this. It is, you may have seen this somewhere, notation in like this for vectors in triangular brackets, I suppose. Have you seen this notation before? No? Okay, that's fine. It's actually not the most popular. The one that we're going to be rely on is in fact this. 1, 3. Have you seen this? Yeah. Okay, so it is the same thing. The only advantage of what's on the left, guess what's the advantage of the one on the left?
It looks like the other, the point form.
Right, it is, but actually, no, not that. The main advantage is that it is just horizontal. So you can fit it in a line. Imagine that you do algebra with those vertical things, especially when they go up to high dimensions. It becomes cumbersome and just too much room, and then so that's the way I see it. That's the only way you're going to go this way from thinking of vectors as columns to thinking of vectors as strings. Okay, so we're going to be dealing with columns and rows, but sometimes just for to keep it more compact, we'll utilize this notation with triangular brackets or this one, which is just parentheses. But usually you think of those as points. The difference, as you can see, they're interchangeable in the sense that if you have a point, it gives you a vector, the end of point of which is your point. Okay, so 1, 3, a point right there, this one. Okay, and then you have a vector from 0 to that point, and that's you can go back and forth literally. But what's the difference between points and vectors? There is a difference. We do geometry with points, and we do algebra with vectors. Okay, so we could do some geometry too with vectors, but if you're talking about things such as distances between points, not distance between vectors. Okay, so sometimes it makes a big difference. Also, you can add vectors. You shouldn't add points. Okay, so if you keep it separate, sometimes it helps you to avoid mistakes. So, okay, so then we already have taken care of x, y. The other The other possibility is, well, to compare these two. Let me move this slightly. So the original is one-dimensional mx equal b. Okay, so it is aligned pretty well. So this is, we already realized that x has become xy, a vector, xy, a column. But then the next step is b. It also becomes vector. Here it is. This is my b, and it's also a vector. Okay, so we are collecting information. So one vector, let me make it capital X. I will use capitals for anything multidimensional. So xy will be my vector of unknowns. Vector of unknowns. Okay, so it's at the same time it is a vector, but remember it's also a point on the xy plane. So all the geometry that we have looked at, intersecting lines, will still be applicable. Okay, so a vector of unknowns, and then I put b. I'll capitalize everything. B is 6, 14. I don't think there is a good word for it. It is just the there are different ways to describe them. Either you say it's the right-hand side of our equation, or you can say these are the free terms collected together in the sense that those terms that are independent of x and y. And what remains is the coefficients. So if we look at at our equation, you can see, so we know x and y, how to collect x, y together. We know what to do with 6 and 14, collect together. But there are a bunch of numbers left. So this is how I would write it. I would write x. Well, let me mark what we already know. X plus, well, we still don't know how to add. So we have xy, 6, 14. Okay, so this is we understand. We know how to collect them together. But what's left is still the coefficients. 1 equal, 2, 3 equal. Okay, so that's the same equation we started with. I just put it in a more way kind of like I'm talking about data rather than something algebraic, because I'm not going to solve it. We already know how to solve it, so that's not our concern anymore. We want to put it in the form that is manageable and something, by the way, that can be handled by a computer. Okay, so we have taken care of the vectors, and now these 4 numbers will be put into what we call a matrix. It's just a table. So 1, 1, 2, 3 is put is put in a matrix. So a matrix of coefficients. So let's call it A. 1, 1, 2, 3. Okay. So as you can see, we have these three. So we had what? We had quantities combined together in 2 equations. The goal is to have one equation which with possibly more complicated entities than just numbers. So that's why we have. I spent a little bit of time talking about functions in general, not necessarily as it applies. The idea applies to numbers, but rather also how it applies to anything else in a totally abstract sense. And right now we will be speaking of functions of vectors. Okay, because as you can see, once again if I scroll back here and to equations that we care about, it looks like this: a linear function on the left, with a number on the right. Okay, so that's what we want to still have. We want to have a linear function of xy on the left, and then that vector b on the right. Okay, so let me just write it out for you how it works. So ax is equal to b. That's what we want. So our equation, our system of equations turns into this. How is explained in a minute, but let's appreciate the thought that it will be exactly the same no matter we have 1 variable, 2 variables, or 100 variables. It will, the matrix form of a linear equation will look exactly the same every time, ax equal to b. And then we want to learn how to solve them, or at least say something specific about it. So, okay, so then let me write it out in terms of the specific vectors and matrices. So 1, 1, 2, 3 times x, x, y is equal to 6, 14. Okay? So we just have to find a way from here to there. All we have to do is to, in what sense A is multiplied by x to produce B. Okay? And the idea you probably can recognize what's happening here. In fact, let me do it this way: 1, 1 over here, 1, 1, x, y. So do you see the first equation there? The first equation on the right. Do you see it at the bottom? One, 1, x, y, 6. You multiply and add, right? You multiply 1 by 1. 1 times x plus 1 times y is equal to 6. I'm seeing that on the right, at the bottom, and it produces the first equation. The second equation is similar. 2, 3 times xy gives me 14. Okay, like this. So it's a weird way to multiply. Certainly, it seems that like a lot of stuff comes into play because well, we have to produce 2 equations from 1, but that's the way it just works out. So anyway, we'll just talk more about this, and the homework one will be assigned on Wednesday. Okay, thank you.